Okay, let's start. So today we're going to conclude our discussion of exploration, and then we'll also begin the discussion of transfer learning, which will continue through next week. But before we start, a few quick class notes. So homework 4 is due next Wednesday, so hopefully all of you are well on your way to getting that done. And then after that, we'll have one last homework, homework 5, which will be on some of the more advanced topics, and then it's just your final projects. All right. That's all for the class notes. Let's conclude our discussion of exploration from last week. So first, a little bit of recap. On Wednesday, we talked about the exploration problem, and we started with a little bit of motivation. We started with a discussion of what the exploration problem really is. And if some of you remember, I showed these videos. I showed the video of the breakout game and said, well, this is something that is actually fairly straightforward to learn. So probably if you were to run your Q-learning code from homework 3, on this game, you would get a pretty decent solution. Whereas this game, which doesn't seem all that different in some ways, is actually extremely difficult to learn. Does anybody remember what are some of the issues that make exploration challenging? What are some of the reasons why some of these settings are much harder to learn than others? Any thoughts? Anyone want to throw out any ideas? Yeah. Long time horizon, right, which means in particular that you might not see a reward until after some long period of time has elapsed. Any other ideas?
Weekly correlated rewards.
Right, weekly correlated rewards. So for example, maybe you do get some rewards here, but the rewards that you do get don't really correlate with the big reward you're going to get at the end. And you could imagine some pathological cases, like maybe someone could make an even harder game where the guy gets a little reward every time he dies, but then a big reward if he wins. So that would cause a really bad local optimum where he just wants to kill himself and doesn't actually ever discover that winning the game is a good thing. So there are all these properties in MDPs that can make exploration extremely challenging. So on Wednesday, we talked about different classes of exploration methods for bandit problems. Bandit problems are kind of the Drosophila of exploration problems. They're the simplest exploration problems that are still meaningful and interesting to analyze. Bandit problems essentially dispense with the notion of time. They only have one time step, and they dispense with the notion of state. So all you do is you just select an action. And we saw that for bandits, we could actually analyze different exploration strategies, and some of the strategies could actually approach the Bayes optimal strategy in the limit. So the kind of exploration strategies we're going to talk about for deep RL problems are inspired by these principled methods from the bandits literature, but in the world of deep RL, of course, the theoretical analysis is not possible, so they're sort of heuristics, but heuristics that we have good reason to believe might work well. And they basically fall into 3 categories. The first category is optimistic exploration methods. So these are basically methods that make the assumption that when you see a new state, a state that is different from states that you've seen before, that is a good thing. You should attempt to see more new states. And this requires us to estimate some kind of state visitation frequency or novelty measure in order to figure out whether a state is new or not, because in big, high-dimensional problems, every state is technically distinct from any other state that you've seen before, so you have to have some notion of similarity. And typically, the way that we bring about optimistic exploration is we use some kind of exploration bonus. So we take the reward function and we add an additional term to it that incentivizes going to new states. We're also going to talk about algorithms for exploration in deep RL that are inspired by Thompson sampling or posterior sampling. So here we're going to maintain a distribution over something. Over what? That's actually a question we'll have to resolve, but maybe it's going to be over Q functions or policies or models, so there are a lot of things that we can maintain distributions over. And then we'll sample from that distribution and act as though that sample was the right answer, and then we'll generate new samples every iteration. And then we'll, at the end, discuss information gain style algorithms for exploration in deep RL. So these are algorithms that actually reason about the information gain that you will have from visiting new states, which is similar to novelty up here, but a little bit different because you're explicitly trying to figure out how much you will learn from visiting a new state, rather than simply assuming that something is good simply because it's new. Okay, so let's resume our discussion of count-based exploration. So this we covered it in a bit more detail on Wednesday, but just to briefly recap to get everyone on the same page. In count-based exploration, you would take your reward function R, and you would add a little bonus to it that depends on the number of times you visited a state. So this is the analog to UCB-style exploration in bandits, but for MDPs. And you can do actual count-based exploration in small MDPs. In small MDPs where you can count how many times you've been in each state, you can just directly calculate n of s and use this method. But of course, for big, high-dimensional decision-making problems of the sort that we tackle when we do deep RL, this kind of counting technique starts to break down because when your state, for example, consists of images, no two images are quite alike, and you have to say, well, are you going to count how many times this guy has been in this place? Are you going to count how many times the skull has been in that place? Like, what is the thing that you're counting? And of course, when your state space is combinatorially large, then simply counting the number of unique states you've seen is not going to cut it. And of course, if your state space is continuous, then all bets are off in that regard. So you never see the same thing twice, which means that what you have to do if you want to adapt count-based methods for deep RL is you have to have some notion of similarity. You have to reason about the fact that if you see a state that you've never seen before, but that is extremely similar to another state that you've seen before, it kind of has a non-zero pseudo-count in some sense. Even though literally its count is 0, it really shouldn't be 0 for the purpose of exploration because you've seen very, very similar states in the past. So on Wednesday, we talked about how we can capture this notion of similarity by fitting a density estimator, p theta of s, to all the states that we've seen so far. And today we'll actually talk about what types of density estimators we might use and what some trade-offs there are. But the intuition here is basically your density estimator, it'll give non-zero density even to states that are not exactly the same as states you've seen before, simply because they're similar. So if you want to imagine a thought exercise here, imagine the simplest density estimator. Imagine that you're just fitting a Gaussian, right? So perhaps this is S, this is P of S, and perhaps you've seen this state, and this state, and this state. If you fit a Gaussian to them, it'll look like this. So it'll put non-zero density on this state and this state, even though they were never part of the data set. So I'll mark them like that, right? So density estimation generalizes, which means that it will give non-zero density even to things that are not exactly the same as the things you've seen before. Okay. So here's how we can design an algorithm that's based on density estimation and on the idea of counts. It's going to sort of generalize the idea of counts to pseudo-counts, and this is what we saw on Wednesday. You fit your model, p theta of s, to all the states you've seen so far. Then you take a step, you choose an action, and you observe a new state, Si. Then you take this new state, Si, you append it to your data set, so you get D union with Si, and you refit your density estimator. Now you have two density estimators. You have p theta of s, which is what you had before you took step Si, and you have p theta prime of s, which is the density that you had after you observed Si and refit your density estimator. And now what we're going to do is we're going to use these two densities to estimate a pseudocount. A pseudocount is a numerical value. It might not be an integer value, but it's a numerical value that sort of obeys the same properties that we would expect a count to obey. And then you're going to use that pseudocount in place of a real count as your bonus. And we talked about how there are a few different choices for bonuses, but basically they all need to be big for small n and small for big N. So a reasonable choice is 1 over the square root of n hat. So now how do we calculate the pseudocount? Well, we're going to write down the kind of equations that we expect a count to obey, and then we'll solve them to solve for the count. So we would expect that a count would be the number of times you've been in that state divided by the total number of states you visited. And after you observe the state, the numerator and the denominator should be incremented by 1. So if you've just visited that state, its count should go up by 1, and the total number of states you visited should go up by 1. So if we're using actual count-based exploration, we would directly keep track of n of s and little n. But if we're doing pseudo-counts, what we would instead have is p theta of s and p theta prime of s, two numbers. And we have two unknowns, which means that we can just do a little bit of algebra and solve for big N hat and little n hat. So two equations and two unknowns. And on Wednesday, we saw these equations for actually solving for the pseudocount. So you just directly plug in this math, get n hat, plug it into the bonus, and just increase the bonus for that state. OK, so this is the method we covered on Wednesday. At this point, we're done with the recap. Any questions? Yes?
Is it numerically stable when you're subtracting something in the denominator for n hat?
This quantity. Yeah, so this is a very good question. For those of you that didn't hear, could there be some problems here because you have a denominator and you're subtracting two values? The answer is that yes, you can run into trouble. The reason that you wouldn't ordinarily run into trouble with this is that you just updated your density estimator at the state SI. So you just added this state SI, updated for exactly that state. So if any value is going to change, it's probably going to be that value. But yes, the answer is that this can get a little bit dicey sometimes. Okay, so now let's talk about the model a little bit. Of course, in reality, you wouldn't use just a Gaussian for doing this. You would want some model that can capture densities on complex state spaces. So what kind of model should you use for p theta of s? There are a few choices. We could, for example, think about the kind of density models, the kind of generative models that we've learned about before. For example, we learned about variational autoencoders. Does anyone have any idea about, any thoughts about what might be good or bad about using, let's say, a variational autoencoder for p theta of s?
How to actually compute the probability for the sample in the variational autoencoder?
Exactly. So the question was, how do you actually compute the probability of a sample for a variational autoencoder? And the answer is, it's very hard. It's intractable. So oftentimes when we use density models, when we're doing deep learning, we make use of latent variable models. And latent variable models, we can train them with approximately using the variational lower bound, but actually computing densities from those models exactly is intractable. And you have to do all sorts of approximations to make that feasible. So the important thing about p theta of s is that we needed to provide densities, but we don't necessarily need to produce really great samples, which is kind of the opposite of the consideration that we usually have in deep learning when we talk about density models. So if you talk about variational autoencoders, generative adversarial networks, all sorts of fancy models that we have in deep learning, those models are great for producing good samples and maybe even learning representations, but they're not necessarily that great for actually estimating the densities numerically because you usually have to integrate out the latent variables, which is intractable to do exactly and requires some approximations. We could still use those models for exploration. We just have to estimate the densities approximately usually by sampling latent variables and then averaging together the corresponding likelihoods. But there are other models we could design that have kind of the opposite considerations, that are good for producing density values, but not good for producing samples. And those we would actually prefer for doing exploration, because when we're doing exploration, we don't need to actually sample from the model. We just need the model to give us a number for the density of a given state. So there are a few choices. There isn't a single great choice, but there are a few choices that have been explored in the literature, and I can tell you about some of the trade-offs. So in the original paper on pseudo-count-based exploration by Bellmer et al., they used a model called the CTS model, which is kind of a funny model that's a little bit tailored to these kind of images, actually kind of Atari-style images. I'll tell you about how this model works, but it's a rather peculiar model. The way it works is like this. You say that the probability of an image is equal to the product of a bunch of conditionals. And each of those conditionals gives you the probability of a pixel given its neighbors to the left and above. Why to the left and above? Well, you can also do to the right and below, but that's kind of an arbitrary choice. The critical thing here is that if you're factorizing a distribution using the chain rule, each variable needs to appear on the left of the conditioning bar only once, and you can't have circular dependencies. So that's why you can't make this thing dependent on all of its neighbors, because then you have circular dependencies. So you have to impose some ordering on the pixels. And the particular ordering they impose is to say, well, let's just make sure it's the top and the left. So for every pixel ij in the image, xij in the image, you have a separate probability of that pixel given its neighbors to the left and above. And then you can represent these factors however you want, and the probability of an image is just a product of all of these things. Which is convenient, because then if you want to calculate the probability of an entire image, you just multiply them all together. If you were to actually sample from this model, you probably wouldn't get very good images, because these are very local dependencies. So it sort of models local interactions between pixels. But if you just want to get a number for a density, this can give you something meaningful. Okay, But we can design all sorts of other models that are maybe a little bit more general in nature that we can use not just for these kinds of images, but also for other kinds of tasks. So here's one idea. This is from a paper by Tang et al. Called count exploration. And here the idea is to use a hash function. So if you have some really high dimensional data, you're never going to see the same vector twice. So if you let's say your state space is in Rn, where n is like 100, if you randomly take vectors in Rn, you're never going to see the same vector twice. But what you can do is you can compute a hash function, and you can choose the length of that hash. So if the hash is short enough, then you'll get pretty frequent hash collisions. So you're still going to count states, essentially, just using regular counts, but now you'll count them in a different representation where states that are a little bit different might still be represented with the same code. So the idea is that you take your state S and you compress it into a k-bit code via some compression function, phi of S. And then you just count how many times you've seen that code. If you pick a short enough code, then you'll get plenty of hash collisions, even for states that are technically all distinct from each other. Of course, how well this idea works depends very heavily on how you're compressing. And of course, you want to compress states that are in some sense functionally similar. If you simply compress states with some arbitrary compression mechanism, you might get hash collisions between states that are not actually all that similar as far as the MDP is concerned. So that's where you can do a little bit of design work. The particular thing that they do in this paper, which is one reasonable choice, but probably not the only choice, is that they actually train an autoencoder model, so a model that maps from the image back to the same image. And this autoencoder model has a bottleneck layer. So the bottleneck layer is basically a layer where they limit the number of units. So they limit it in this case to 512 units. And from those 512 units, they actually compute the hash. So they take that 512 length code, run it through a regular hash function, just a standard hash function that you would use, for example, to compute a file hash, and they get a binary code, which they can then keep a count on that. So the smaller your code, the more collisions you get, meaning the more this model generalizes. Then you have to tune the length of the code and the architecture of the autoencoder. Question?
So this doesn't sound like locality-sensitive hashing. It sounds just like plain hashing.
Right. So in this case, there's actually no accounting for like the dynamics of the MDP, for example. There are other things you could do, which these guys didn't do, but you could. You could, for example, instead of training an autoencoder, train this model to predict the next frame. And then you might expect the bottleneck layer to capture something that is relevant for prediction, which is maybe a little more dynamics aware. And then you can go and hash that. That's a design decision. So these guys just directly train an autoencoder, but you could train other kinds of models. And they observe that indeed their hash thing, which is, well, let me actually explain what's going on here. So the blue line here shows hashing on top of the autoencoder state. The red line shows a hash computed on top of the image pixels, and the green line, I'm not actually exactly sure what that is. But you can see that in most of the cases, the blue line is actually performs pretty well, although even just hashing the pixels generally results in a substantial improvement over the orange line, which is where you have no exploration. So the red is the pixels, and the blue is the method with the autoencoder. So something meaningful is happening there with counting the hashes. Does anyone have any other questions about this work? Okay. So the next count-based method I'm going to discuss actually takes a slightly different approach to computing counts, but based on the same general principle that you want a P of S where it's easy to get densities and where you don't necessarily need to get samples. So the idea in this work, it's a little bit different. The idea is, well, maybe one good way to determine if a state is new is to try to see how easy it is to distinguish that state from states you've seen before. So if you've seen like millions of frames of Montezuma's Revenge with a guy jumping up and down on the ladders and so on, perhaps another frame that's not exactly the same as those previous frames, but in the same room, maybe it's a little bit difficult to distinguish. But if suddenly the guy goes into a different room, now it's really obvious that this frame is different just by looking at the color of the background, for example. It's just a completely different frame. So perhaps if you train a classifier to distinguish the frame you're seeing now from past states that you've seen, the difficulty of training that classifier somehow reflects the novelty or lack of novelty in the state. If it's really easy to train a classifier to distinguish the new state from old states, then this new state is probably pretty novel. And if it's really hard to train that classifier, if the classifier is not very accurate, then perhaps the state is not so novel. So the intuition is that the state is novel if it's easy to distinguish from all previously seen states by a classifier. And in particular, if you make that classifier somewhat weak, if you regularize it, then this can give you a relatively smooth measure that also generalizes across states. So the procedure is actually going to be based pretty much exactly on this. I'm going to outline it here, and it's going to seem kind of really expensive and intractable, but I'll explain how to make it tractable in a second. At a high level, the procedure is that for each observed state, you fit a classifier to classify that state against all past states that you've seen. And then the classifier error can actually be used to obtain an estimate of the state density. So let's not worry about how it's really expensive to train 1 million classifiers. Let's just assume that we can train these classifiers and figure out how we can use them to obtain densities. So the punchline, which I'm going to give away now, but I'll derive it on the next slide, is that if you have a classifier, ds of s, and this classifier tries to distinguish the state s from all past states that you've seen, so positives are s, negatives are everything in the data buffer, then this ratio actually gives you an estimate of the density of s. So d of s here is the probability that the classifier assigns the positive class to s, where it's trained, where the positives only include s, and the negatives include everything in d. Okay, it might take a second for it to sink in what exactly this is saying. And once it sinks in, it might be obvious that this is actually a little bit weird. It's actually extremely weird. Because if you're asking this classifier to tell you if the state s is equal to the state s. And that's kind of silly, right? So the positives for this classifier include only s. The negatives include all the states you've seen. So asking it to classify s basically amounts to asking it to answer the question, is s equal to s? That's kind of strange, but there's actually a little nuance. You see, if you're in a tabular or discrete state space, where the number of states is relatively small, then if the state s has been seen many times, it'll appear in the data set. And remember, the negatives consist of all the states in the data set. So in reality, if you have a small state space, then your data set D, which comprises the negatives, will contain the state S also. So the positives consist only of S, and the negatives consist of a whole bunch of states, which might also include S. So in fact, this classifier is not just saying, is S equal to S? It's actually trying to figure out how often does S actually appear in your data set. So if S never appears in your data set, then of course it will have a very easy time answering this question. It will just say 1.0. But if S appears in the data set also, then it'll have a bunch of negatives that are S and a bunch of positives that are S, and we'll have to output a fraction. So the optimal classifier is not, in fact, going to always output 1 for S itself, because S might appear in the negatives. And in particular, how many times? What is the value that the classifier will output? Well, it will actually output the ratio of the number of times that S appears in the positives over the number of times it appears in the positives and the negatives. And since it appears only once in the positives, the answer is to output 1 over 1 plus the probability of S, where the probability of S is the fraction of your data set that consists of S. So in small, countable, discrete spaces, the optimal classifier is 1 over 1 plus P of S, and then you can do a little bit of algebra to show that this actually directly implies that P of S is equal to 1 minus D over D. So that just implies that just consists of solving for P of S. Now that's what happens in small, discrete state spaces, where the state S is visited many, many times. So this just shows that counting and fitting this classifier are actually going to do the same thing. They're going to give you the fraction of the data set that consists of S. In large or continuous spaces where you never see exactly the same state twice, of course you have to rely on your discriminator, on this classifier, to actually generalize in some meaningful way. And generalize here means that it will not classify perfectly. It'll actually make mistakes, and the kind of mistakes it'll make are that it will confuse states that look similar to S with S itself. In order for this to happen, of course, you have to regularize your classifier. So in reality, each state is indeed unique, so you have to regularize the classifier so that it doesn't overfit completely and doesn't memorize S and just do an equality comparison. And there are a number of ways that you can regularize your classifier. The simplest ones are to limit the size of the network or to use weight decay. But there are also fancier ways of regularizing your classifier. And if you want to read about those, you can check out the paper and read about something called the information bottleneck principle, which basically restricts the channel capacity in the hidden layers of the classifier. So there are a few ways to regularize. But the point of all this regularization is to make the classifier resistant to simply memorizing S. Does this trick make sense to everyone? Does anyone have any questions about how we can recover densities from classifiers? Okay. So the last question I want to answer about this method is, well, this all relies on training a separate classifier for every single state, because that's how we're going to get densities from those states, which is how we're going to get counts. So isn't that a bit much? You know, maybe you visited 1 million states, that means you have to train 1 million classifiers. So what we can do is we can actually have just one neural network that sort of acts as a universal classifier. Because these classifiers are a little special. You know, each classifier has the positives consisting of just one state. So what we can do is we can just input the positives directly into the network. We can have a network that takes in 2 inputs instead of 1. The image that you're trying to classify and the image or state that corresponds to the positive set. And that's what we're going to do. We're going to have a network that takes in, for some state X, it takes in the state that you want to classify and the state that you want to classify it against. So you can think of this almost as a learned comparator. Equivalently, you can think of it as a classifier conditioned on the positives. And then you just train one network. So that becomes much more tractable. So if you do this, you can actually get pretty decent exploration. And this kind of approach can be particularly desirable if your inputs are very high dimensional. Because if your inputs are very high dimensional, then trying to explicitly model the density of the inputs might be very hard. But trying to train classifiers on high dimensional inputs, that's pretty easy. So that's basically what all of supervised deep learning is concerned with. If you have image inputs, then convnets can work very well for that classifier. So these results in particular are for an image-based navigation task for a benchmark task called VizDoom, which is based on the game of Doom, where the goal is to navigate this maze, to go through a sequence of rooms starting over here and ending over here. And of course, the exploration challenge here is that you don't receive the reward until you actually find the exit, which means that the exploration bonuses have to incentivize you to go from one room to another until you arrive at the exit and actually receive the reward. And in these curves, the blue curve is showing what happens if you use this kind of network where you have one network conditioned on the positives. The orange curve shows what happens if you actually train a separate classifier for every state. There, in order to make this even remotely tractable, the classifiers actually share the convolutional layers, but they have a different linear layer at the end. And then red is showing a method called VIME, which we'll talk about later, and green is a baseline without exploration. Okay, does anyone have any questions about this method? Yes?
I didn't quite understand how you train this. Basically, each state that you feed as your first one is also a part of your data set, or is it like...
Right. So here, let me kind of draw it on the board a little bit. Let's say that you live in a world where there's just 4 states. So the set of states is A, B, C, D, right? Just 4 states. And now you've been exploring this MDP, and your data set consists of A, B, C, D, D, right? And now I'd like to figure out what's the probability of A. What's the density of A, P of A? What I can do is I can train a classifier where the positives include just A, so D+, and the negatives consist of the entire data set. Now, this classifier cannot get 100% accuracy because there are 2 A's with negative labels and 1 A with a positive label. I'm going to balance this. I'm going to give them equal weight, so this is going to be A repeated 6 times so that it's the same size. So now when I train a classifier on this, the set of positives includes 6 A's. The set of negatives includes 2 A's and 4 things that are not A's. So that means that it's going to output, I guess, D of A is going to be, what, 6 over the total, which is, sorry, 8 over the total, which is 12, right? Yeah. So it's going to be that, which is less than 1. If there are no A's in here, then it would output 100%. All right. So now let's move on to the next class of exploration methods, which is based on posterior sampling or Thompson sampling. So as a reminder, when we talked about exploration with posterior sampling or Thompson sampling for bandit problems, the idea was the following, that your bandit problem has some probability of outputting a reward R subscript theta of A for the action A, and that reward is, it's dependent on some probability distribution parameterized by theta. So what you can do is if you have some prior on theta, P of theta, you can maintain a belief over theta, and that belief is going to be denoted with P hat. So for example, if we think back to the drug prescription problem that we had on Wednesday, each of those drugs had some probability of killing the patient, which is just a number, theta I, between 0 and 1. So you could explicitly try to estimate theta I for each of the drugs. Of course, you don't know exactly what theta I is, so you maintain a belief about it. If you've never tried to prescribe a drug, perhaps it's just a uniform distribution between 0 and 1. If you've prescribed that drug many times, and each time the patient died, perhaps it's very peaked at 0. And then the way that you actually do exploration with posterior sampling or Thompson sampling is that you sample from your belief to get a vector of thetas, pretend those thetas are correct, and then take the optimal action. So if we want to apply this to deep RL, we have to answer a few questions, like what is it that we're going to sample now? Because for deep RL, there's more than just rewards, there's also dynamics and so on. And how do we represent the distribution over our beliefs? So in the bandit setting, P hat of theta 1 through theta n represents a distribution over rewards. So what's the analog in the world of MDPs? Well, there are a few choices. But one thought that we could have here is, well, the rewards in a bandit setting give you, they basically exactly tell you which action to take, because you always take the action with the biggest reward. So in RL, there is kind of an equivalent, but in RL, the equivalent is not the reward, because in RL, rewards are temporally extended. The equivalent is actually Q functions. Because just like in the bandit setting, if you know the reward, you just take the action with the biggest reward. In RL, if you know the Q value, you take the action with the biggest Q value. So if you maintain a distribution over Q functions and you sample Q functions, then that directly tells you immediately how you should act in the world. So let's think about whether we can do exploration by maintaining a belief over Q functions. So the procedure will be analogous to the bandit-based posterior sampling, except now we'll just have Q everywhere where we had R before. So step 1 is you're going to sample your Q function from your distribution over Q functions. Step 2, you're going to pretend that this Q function is correct, and you'll act according to that Q function for 1 episode. And then step 3, you're going to update your distribution over Q functions. And then you'll just repeat. So this is basically the equivalent of posterior sampling, but for MDPs, simply replacing rewards with Q values. And of course, since Q learning is an off-policy algorithm, it's actually perfectly fine that in step 2, we're acting according to only 1 out of the many possible Q functions. We can still use all that data to update our distribution over Q values because we're going to be doing off-policy learning. So the only thing that we care about in step 2 is that we should actually explore effectively. We don't really care about which particular policy we're running because it's an off-policy algorithm. So the procedure is actually very simple. The main question we have to answer is, now we need this distribution over Q values instead of a single Q function. So how can we represent a distribution over Q functions? So let's say our Q function is a neural network. How do we represent a distribution over neural networks? Does anyone have any ideas? How can we represent a distribution over neural networks?
The distribution of the weights.
So one answer is perhaps you have a distribution over the weights in the neural network. That's on the right track. Is there anything we've seen before that can help us? Any tool we learned about in a previous lecture?
Yeah, we say that every weight is a distribution.
Mm-hmm. Right, so when we talked about model-based RL before, we talked about Bayesian neural networks, where you actually have a distribution over every weight. We also talked about another way that we can estimate distributions that's a little bit simpler, which is to use bootstrap ensembles. So you can either have a distribution over every weight, or you can actually keep track of multiple parameter vectors that are trained with bootstrap ensembles. And indeed, both of those techniques could be used to get a distribution over Q functions. So I'm going to talk about a particular paper called Deep Exploration via Bootstrap DQN, which is one instance of posterior sampling or Thompson sampling for exploration RL. And this one makes use of bootstrap ensembles. You could very likely also do this with Bayesian neural networks. So if you want to do it with bootstrap ensembles, then you take your data set, which in Q-learning is the data set of all transitions that you've seen before, and you're going to resample it with replacement n times to get n distinct data sets. And those data sets, you can think of them as basically the original data set where each data point gets an integer multiplier that goes from 0 to n. And then you're going to train each model, which in this case is going to be a Q function, on its own data set. And then if you want to sample from the distribution over model parameters, you just pick a value from 1 to n and use the corresponding model f theta subscript I. That's it. Very simple procedure. So in this paper, they actually have a little bit of an illustration trying to figure out whether this bootstrap ensembles method actually does produce reasonable uncertainty. So this is not Q-learning, this is just a 1D function. And they're comparing to a Gaussian process, which is kind of the gold standard for Bayesian nonparametrics for providing good uncertainty estimates. And they show that their ensemble does provide good variance estimates. So the way that you read plots like this, if you ever see a picture like this, the thick gray line shows the mean, and the shaded region shows, in this case, I believe, 1 and 2 standard deviations. So you would expect that in regions that are far from the data, like here in the middle, the standard deviations should go up. So indeed, it does seem to be doing that, not quite the same as the Gaussian process, but something reasonable. So that's a good sign that maybe there isn't a bug in the code. That's good. So when you go and train this thing, if you want to actually do Q-learning for some really complicated tasks, like image-based reinforcement learning tasks, then it can actually be quite costly to train n completely separate networks. And in fact, the number of networks n that's actually a very sensitive parameter of the method, because you get better uncertainty estimates the bigger n is. So perhaps one way that you can get larger values of n is by not having the network be completely separate for every single bootstrap, but instead having it share some layers. And that's what they do in this paper. So they actually have a convolutional network, but almost all the weights are actually shared, and then the network has multiple small, fully connected heads at the top for each of the bootstraps. Now, once you start doing this, the nice, convenient theoretical guarantees of the method actually disappear, because the network can learn some internal representation that is already very close to the Q values. But in practice, they find that this does give them some reasonable uncertainty estimates. But at this point, it's a heuristic approach. And in fact, as I discussed when I talked about bootstrap ensembles in deep learning back in the lecture on model-based RL, this particular resampling step actually turns out to often be unnecessary when we're using deep nets, because deep nets are already going to be different from each other when they're trained multiple times because of the randomness of stochastic gradient descent and the sampling of the mini batches and the weight initialization. So for this reason, when they actually conduct their experiments, they simply don't do this. And they just use the same data set with different batches sampled for each head and different initial weights for each head. Okay, so that's the method. And the basic principle behind it is essentially the same as posterior sampling for bandits. But we can also try to get a little bit more intuition about why we expect something like this to work. So first, what's the bad thing about not doing this? If you're not doing this and you're doing, let's say, epsilon greedy, then exploring with random actions basically means that at every time step you either take the greedy thing or you take an action that is independent from the previous action, which means that you can kind of oscillate back and forth. And there are some settings where you're extremely unlikely to do the right thing if you take independently random actions at every step. So here's an Atari game that you guys can go back to homework 3 and load it up. This one, I like this game a little bit better than Montezuma's Revenge. It involves piloting this little submarine, which for some reason is supposed to shoot the fish. I think this is not very ecologically friendly. So you're supposed to shoot the fish and then save the divers. Maybe if it was more ecologically friendly, it would actually be the opposite. But anyway, the challenge with this game is that you'll go down to the bottom of the sea and you'll be happily shooting all the fish and destroying the ecosystem, but you're running out of oxygen right here. And if you run out of oxygen, you will lose the game. So what you have to do is you have to shoot the fish and then come back to the surface to replenish your oxygen. And it's actually easier to shoot the fish if you're further down at the bottom. The trouble is that if you're at the bottom, if you want to come up for air, you have to repeatedly push the up button. And if you don't know yet that you have to come up for air, you're relying on random exploration to come up for air, you have to basically have this epsilon greedy strategy, randomly choose to push the up button multiple times in a row, which becomes very unlikely the deeper down you are. So epsilon greedy exploration for this game actually has a lot of trouble coming up for air. So it'll become a champ at shooting the fish, but it will suffocate on the first oxygen tank. If you do bootstrap Q learning, then what will happen is that your Q functions, many of them will not actually realize that you have to come up for air, but one of them might just randomly be a little bit biased towards going up. And because you execute the same Q function for the entirety of the episode, once one of those Q functions randomly decides to prefer the upward action, it will actually start coming up for air. And because all of the Q functions then share the same data, as soon as one of them randomly comes up for air just because it's biased to pushing the up button, they'll all start learning to come up for air. And then you can shoot the fish and come up and recharge your oxygen. So that's basically the idea, that once you commit to a particular strategy, to a particular Q function for the duration of the episode, you get much more structured exploration that can overcome this challenge of needing to push the up button randomly multiple times in a row, which of course becomes exponentially unlikely in the naive case. And indeed, you see that this method here, red shows the bootstrap DQN, and green shows the vanilla version. It does do better on many of the games. It doesn't do better by a huge margin, but it gets like a fairly consistent medium to small to medium improvement. So maybe at this point we might ask, well, what are the trade-offs between doing this type of exploration versus the count-based or bonus-based exploration I discussed before? One very nice thing about this class of exploration methods is that you're not really changing anything about the problem. You're not changing the reward function. All of these Q functions are trying to solve the original problem. And you're not introducing sort of a heuristic preference for new states simply because they're new. So you could imagine that there might be some pathological MDPs where there are many states that are novel and interesting, but completely unrewarding. You know, perhaps it's Montezuma's revenge, only winning the game doesn't actually get you the reward. And in fact, the right thing to do is to just stay in that original room. A novelty-based method would, of course, go and explore the whole space before realizing this, but a method that is based on uncertainty about the Q values wouldn't be distracted by that, because it's not really paying attention to states simply because they're new, it's paying attention to Q values. The downside is that for problems where novelty does provide a good exploration heuristic, these kinds of methods generally don't do quite as well. So a very good exploration bonus method will often do better, except in these kind of pathological cases where novelty is actually bad. So that's why if you look at the results in this paper, they're maybe not quite as impressive numerically on the Atari games, because just because of how we build video games, in Atari games, novelty is actually a very good cue for exploration, because in most Atari games, going to a new level is a good thing. That's not necessarily true for all tasks, but in games, you wouldn't make levels that you're not supposed to play, because that would be just a waste of time. So partly, the benefit of exploration bonuses is a little bit of an artifact of how these games are built. Okay. The last exploration technique I'm going to talk about is based on information gain, but at this point, I think we're going to take a little break, and we'll resume at 10:55. So see you all at 10:55 to talk about information gain.
It seems the submarine never go down to the bottom. Yeah.
You mean this thing?
Yeah.
Yeah, well, and in fact, that's probably a better strategy, actually, if you know that you need to come up for air.
Yeah.
Because if you're down here at the bottom, you can collide with all the fish on the way up.
Yeah.
So it does end up with a very different strategy once you learn that.
Oh,
yeah. And this is, partly the reason I picked this game is because this setting is especially pathological, because if you don't know to come up for air, it is actually better to go all the way down, which actually exacerbates the problem. It actually makes it harder to discover.
Yeah. Thank you.
Mm-hmm.
This you adjust this reward function by adding these bonus sets.
Mhm.
Aren't you kind of confusing the agent because like it has states, action, and its next states
Yeah.
which have different rewards, and
Yeah.
then even you're sampling from reward, you're basically averaging them out.
Yeah.
So isn't this like
Yeah,
confusing?
so that's sort of what I meant when I said that for the
Ah.
bootstrap method, it's nice that you're not changing the reward function.
Yeah.
In practice, most reinforcement learning algorithms are okay with that, but it definitely adds to the complexity. It also matters which reinforcement learning algorithm you use, because if you use, let's say, policy gradient, you take your batch, you annotate it with reward bonuses, improve your policy, then you don't revisit that again because it's on policy. So there it's maybe a little bit better. With Q-learning, you do have these bonuses and different states have different rewards at different points in the learning process. It seems to work out, but you're right that potentially you could get these issues.
And one other thing is that like all of these uncertainty estimates
Mhm.
can be used. So in the previous lectures, we used them to reduce overfitting, for example, right? But in here, we're using them in order to get like this novelty measurement,
Yeah.
like the if you have distribution mismatch between your thing, or if your functional approximator was trained on a different support. Can we use them like in this case, like if you're trained something on something that didn't cover the support that you're going to test it on? Can we like get an estimate of how we can trust this neural net in the new regions?
Yeah, you can do things like that. There is some work that has used bootstrap ensembles for Q functions to get at this point. One that comes to mind, and this is a little bit of selection bias because it's a paper from a person I worked with. It's called Leave No Trace by Ben Eisenbach. I'm sure it's not the only one. I'm sure there's others too, but that's just one that I know of. And there Leave No Trace by Benjamin Eisenbach. And he used bootstrap ensembles actually for a safety mechanism. So he has a policy that's meant to reset the system in a safe way, and he used bootstrap to figure out whether there's high uncertainty in the Q values, which indicates that you might be in an unsafe region.
So you're saying if we haven't actually like trained the same support, we can recognize that beforehand. Okay, using this.
All right, let's continue. So in the second half of today's lecture, I'm going to conclude our discussion of exploration by talking about information gain, and then, time permitting, we're going to start our discussion of transfer. So there was a third class of exploration methods that we discussed when we talked about bandits, which are exploration methods based on information gain, which is essentially Bayesian experiment design. You have some piece of information that you'd like to learn something about, which in general we might call Z. You have some observations, which we're going to call Y, and you believe those observations will tell you something about Z. So then what you're going to do is you're going to choose the action A that you expect might produce observations that you expect might help you learn more about Z. And this is actually quite subtle because you don't necessarily want to take actions for which you know which observation you're going to get, because if you know which observation you're going to get, you're probably not going to learn much from it. So on the one hand, you want to take actions for which the observation is uncertain, but on the other hand, you want to take actions for which actually observing that observation, resolving that uncertainty, will help you learn something that you actually care about. So just like in the bandit setting, we have to answer the question, well, what is it that we want to gain information about? What is Z? What is it that we want to learn? And there are a few choices. So you could, for example, say, well, maybe I want information gain about my reward function. That maybe makes a lot of sense. The reward function is what you're really after. In practice, though, asking for information gain about the reward function in many cases might be a little too weak, because if your rewards are very sparse, perhaps there's simply nothing that you can do that you expect to give you information gain about the reward. Because if there was, you would have probably already done it just to maximize your expected reward. So if your rewards are very sparse, if you're not seeing the kind of rewards that you want to see, asking for information gain about the reward might not help you, because you might just not have a good idea for how to gain information about reward. Yeah, one kind of weird thing you could say is you could say, well, what if I'm going to ask to gain information about the state distribution? So what if I want to gain information about S? That's a little bit weird, because like, what does it mean to gain information about S? It's like, learn what states your policy visits. It's a little weird, but it actually kind of makes sense. And I'm going to tell you about a method on the next slide that actually does make use of information gain about S. But perhaps a more conventional thing, and this is what I'm going to spend most of the time talking about, is information gain about the dynamics, about S prime given S comma A. Information gain about dynamics is not exactly what you want, because what you really care about is rewards. But the nice thing about information gain about the dynamics is that it's relatively easy to get a learning signal out of it, because everything you do involves interacting with the dynamics, and interesting events might kind of violate your expectations about the dynamics. So if you if you haven't ever transitioned out of the first room in Montezuma's Revenge, then maybe your estimate of the dynamics might not realize that it's even possible to go from one room to another. So as soon as you enter another room, you might see that there's a lot of information gained from that. So it's a proxy for learning the MDP, but it's still a heuristic because in the end, there might be a lot in the dynamics that you don't care about. So it's a heuristic, but it turns out to be a pretty decent heuristic in many cases. Now, there is a little bit of bad news about information gain, which is that actually calculating information gain exactly is generally intractable unless you have small countable state spaces, regardless of what you're estimating. But there are some good approximations we can use that can actually make it practical to use sort of information gain inspired methods in practice. So here are a few approximations. One approximation, which is a rather crude approximation, is sometimes referred to as prediction gain. It simply approximates information gain as the difference between the probability of the thing you want to learn about, which is z, after an update minus its probability before an update. This looks a little bit like what we saw with pseudo-counts. You're basically updating your density estimator, p theta of s, and then you're using the difference between the log probabilities after the update and the log probabilities before the update. This kind of technique has been used to crudely estimate information gain about states. And the intuition here is that if you just visited a state that you haven't visited very much and you update your density estimator, then its log probability will change a lot. And if you just visited a state that you visited many times, then its log probability will not change a lot. So this difference can be a crude approximation for information gain. And if you want to read more about that, there's a paper by Schmidt-Huber that I'll have a reference to at the end of this section. And the pseudo-count paper by Belmir et al. Also talks about this technique. I'm not going to go into too much detail because I want to mainly focus on the other kind of prediction, which is prediction about dynamics. But the intuition here is that if the density changed a lot, then that state was probably different from states you've seen before. Okay, so let's talk about transition dynamics and variational inference. So this is going to cover a paper by Ray and Huhoft et al. Called Variational Information Maximizing Exploration, or VIME. And there are a few ideas that we need in order to first set up this method. So the first idea is that if you want to measure information gain about z from observation y, it turns out that this is actually equivalent to using the KL divergence between the probability of z given y and the probability of z without y. You can work this out as an exercise on your own just from the definition of KL divergence. But basically, if you can estimate z given y and p of z and compute their KL divergence, you can get information gain out of this. And now we're going to learn about transition probabilities, which means that our z is going to be something that tells us how st and at causes us to transition to st plus 1. So what is the thing that tells us how st and at produce a transition to st plus 1? Well, it's the parameters of this distribution. So it's not actually st plus 1. We're not trying to get information gain about st plus 1. We're trying to get information gain about the model. So we have some estimator for this probability, maybe a neural net. That neural net has some parameters theta, and we're trying to learn about those parameters. So z is actually the parameters of our dynamics model. This is a little bit of a subtle idea. It's actually quite different than what we have up here. And then the observation we get, well, what is the observation we use to improve our dynamics model? It's the transition. So y is going to be a transition tuple, st, at, and st plus 1, which means that we're going to try to figure out whether transition tuples are informative for helping us gain information about the parameters of this transition model, which are theta. So then what we can do is we can plug in this thing for z, this thing for y, and write out that KL divergence. And we're going to add one more thing here, which is h. H represents the history of all the past transitions you've seen. Because of course, you're not estimating theta just from a single transition, you're estimating it from a single transition plus everything you've seen before. So we just have to put that in there. H for history represents all the past transitions. So information gain is equal to the KL divergence between the probability of a given parameter vector for your model, given your history and a transition, against the probability of the parameters given just the history. So theta is the model parameters for your transition probabilities. here you have the newly observed transition, and then h is the history of all prior transitions that you've seen. So if you can calculate this quantity, you can get information gain. All right, so now we have something to work with. Unfortunately, this is still horribly intractable because this requires us to actually maintain a distribution over parameters of a model. And if the model is something like a neural net, of course, we might have a very large distribution. But we've seen things like this before. We saw them before when we talked about bootstrap Q-learning. We saw them before when we talked about Bayesian neural nets. So there are a bunch of approximations that we can use to approximate distributions over parameters. So the intuition here is that a transition is more informative if it causes your belief over theta to change, if it causes your probability of theta to change. And although you can't calculate those probabilities or those beliefs exactly, you can use something like, for example, variational inference to estimate a distribution over theta by using some variational distribution Q. And in particular, this variational distribution Q will have some parameters. We're going to call those parameters phi. And what we're actually going to do is we're going to be updating phi. So in practice, at a mechanical level, the way this algorithm works is that each time it observes a new transition, it updates the parameters of this variational distribution, phi, to get new parameters phi prime, and then it's going to compare phi and phi prime as a way to estimate the KL divergence. So let's go into this in a little more detail. We're going to be using variational inference, which we learned about before. So in variational inference, you don't optimize P of theta given H directly. You optimize some variational distribution called Q, and that distribution has its own parameters, which we're going to call phi. So how do we actually represent Q of theta given phi? Well, for this, there are, of course, many choices for this, but we're going to go back to that thing we discussed for model-based RL, where we have a little Gaussian distribution for every weight. So this is what was mentioned before, too, when we talked about bootstrap Q-learning. There, we opted for the bootstrap. Here, we're going to opt for the other choice, which is to have a little distribution over each parameter. So in particular, in a regular neural net, you have a weight on each connection. In a Bayesian neural net, you have a little distribution over the weight. And you just pick some tractable distribution class. So for example, you might say that P of theta given a data set is a product of independent probabilities on each weight. That's an approximation. It's a very crude approximation, but it makes it tractable. And the particular form of P of theta I given D might just be a Gaussian. So if each parameter theta I has a mean mu I and a variance sigma I, then phi, which are the parameters of Q, just represents the means and the variances. There are other choices you can make for these distributions, but representing your weight distribution as a product of independent Gaussians happens to be particularly simple and leads to some very convenient and tractable algorithms. So we're going to represent theta given phi as a product of independent Gaussian parameter distributions. And then in order to train phi, we're going to optimize the variational lower bound, which is the KL divergence between theta given phi and P of H given theta times P of theta. What is P of H given theta? Does anyone have any thoughts on how this is represented? So H consists of all of the transitions you've seen so far. So P of H given theta is going to be a product over all of the transitions you've seen so far with the probability of that transition given theta. And since theta represents the parameters of a transition model, that's simply the probability of st plus 1 given st under the parameters theta. So you literally just plug in st into a neural network with parameters theta and get back a distribution over st plus 1. So this is basically just the likelihood of your data set. And this is a prior on the weights. And the prior on the weights might just be a zero mean Gaussian with variance 1, for example. So the particular method for optimizing this lower bound you can find in this paper by Blundell et al. Called Weight Uncertainty in Neural Networks. But there are also other ways of training Bayesian neural networks, and we talked about some of those when we discussed advanced model-based RL. So a number of different ways of doing this, but the basic idea is always the same. You maintain a product of independent Gaussians as your distribution for the weights, and then you train it by minimizing the scale divergence, which corresponds to the expectation of the likelihood and the prior. So when you get a new transition, all you have to do is you have to update phi, which means that you take your old phi and you train it some more with gradient descent with this additional transition added to your data set. Very similar idea to what we had in count-based exploration. You see some new data, you update your model, only in this case, the model actually gives you a distribution over the parameters for a transition model. So this corresponds to updating the network weights. And then, since we saw before that we can use KL divergence as the information gain, then your approximate information gain is just the exact information gain for the Qs. So what we want is we want to have the KL divergence between the Ps, but that's intractable, so we're going to do KL divergence between the Qs. And in particular, it's Q theta given phi prime, which is the updated phi, against Q theta given phi. So this is actually looking at the differences in the parameter distributions. It's not looking at the differences in the state probabilities or the transition probabilities, it's looking at the differences for the actual parameters. Which is a pretty interesting idea if we actually think about it, because you're not actually trying to see whether you visited a new state or transitioned in a way that you didn't expect. What you're looking for is whether your model changed in a meaningful way. So you might actually have some unexpected transition, but your model might not change, maybe because it is unable to model that transition, right? Maybe the transition was just random. And that's the big difference between information gain and simply looking for novelties. That information gain looks for things that are new but also learnable, in the sense that they make a quantifiable change to your parameter beliefs. Whereas novelty simply looks at things that are new, regardless of how easy they are to predict or model. Does anyone have any questions about this? Okay. So we can look at some results for this method. So here what they actually do is they test this algorithm on continuous control tasks, similar to the ones that you used for homework 1 or homework 2. And here, when you look at this, the orange line is the one for their method, and the blue line is the baseline without the information maximizing exploration. So you can see that it produces some significant gains in terms of learning speed on a bunch of these tasks. What are some considerations for this class of algorithms? Well, they have kind of an appealing mathematical formalism, at least in my opinion. Like you kind of, in some sense, the derivation suggests that this is a very reasonable thing to do. You're looking for gain in information about things that are actually learnable, rather than things that are merely different from what you've seen before. However, the downside is that this kind of modeling tends to add complexity, meaning that you have to make a bunch of approximations along the way. You have to use variational approximation. You have to somehow model the distribution over parameters. That complexity can make it hard to implement, and it generally makes it harder to use effectively because each additional approximation also adds some additional hyperparameters that you have to select. So there's some very appealing mathematical formalism here. In practice, can be a little tricky to use properly. That said, the basic idea underlying the method is actually one that has appeared quite often also in the past in previous literature, which is if we kind of don't worry about the information gain but focus more on the intuition being that your model has changed in some appreciable way from seeing new data, that intuition can actually be very useful, and you can formulate much simpler methods just based on the intuition, but dispensing with the information theoretic formalism. And that idea basically is reward states where your model changed. So some examples, this is a paper by Bradley Stady and collaboration from 2015, where they encode image observations using an autoencoder and then build a predictive model on the autoencoder latent state. And then you can look at errors from that model as your exploration. There's some older work by Jürgen Schmidt-Hubert colleagues called A Formal Theory of Creativity, Fun, and Intrinsic Motivation, which is a rather fancy name, but the idea is actually based on this intuition also, but predates this work by quite a bit, where the idea is to explore different kinds of exploration bonuses, including model error, and even exploration bonuses based on the size of the model gradient, because the size of the model gradient intuitively tells you how much is the model changing from observing this data point. And there are many other variations, and also many other works that explore similar principles, basically looking at exploration by rewarding transitions or states where some kind of model, either a transition model or a density model, changed in a significant way. All right, let's recap the classes of exploration methods that we've seen for deep RL. We talked about optimistic exploration with counts or pseudo-counts. We talked about different models for actually estimating the densities and the kind of considerations that we have to have for choosing those models, which are a little different than conventional density models in deep learning. We don't care about their ability to generate samples, but we care about their ability to generate good density estimates. We talked about Thompson sampling style algorithms. So these are methods that maintain a distribution over some kind of function, like a Q function or a policy. And we saw how we can, in particular, maintain a distribution over Q functions via the bootstrap, and then sample from that to explore. And we talked about information gain style algorithms, which are intractable in the exact setting, but you can have some convenient variational approximations to information gain, and you have to, of course, choose what it is that you're going to gain information about. And one very convenient choice is to gain information about the parameters of a transition model. All right, if you want to learn more about exploration, some suggested readings. This is the paper by Jürgen Schmidhuber on curiosity. So this is kind of a good reading on, for example, some of these not quite information gain, but intuitively similar principles. This is the Bradley-Stady paper that I mentioned. This is the Bootstrap DQN paper by Ian Osmond. This is the variational information maximization exploration. This is the count-based or pseudo-count-based method. And actually, this is quite a nice paper if you want to read it to get background both on count-based exploration and also some perspectives about how count-based exploration relates to other techniques. This is the hashing-based method that I mentioned. And this is the method based on training discriminators to classify new states against old states. So this will be in the lecture slides, and you can check out some of the suggested readings if you want to learn more. We already had the break. And then in the last 15 minutes, what I want to do is I want to start off by motivating some of the discussion of transfer learning. We're going to start by talking about transfer learning today, and we'll actually have 2 lectures on transfer learning, multitask learning, and meta learning next week. So today we'll have some initial discussion of this, and we'll really get into it next week. So when we talk about transfer learning, we're going to focus on the following. We're going to talk about the benefits of sharing knowledge across multiple tasks. So far we've always talked about reinforcement learning in the setting where you have one task. Now we're going to talk about what happens if you have multiple tasks and you want to share knowledge between them. We're going to discuss the transfer learning problem in a reinforcement learning context. We're going to talk about it in a setting where you have a single source and a target domain, and we'll also talk about it in multitask settings where you have many different domains and you're transferring to a new domain. So let's get started on this a little bit. Let's go back to this Montezuma's Revenge game, the game that if you try to learn from scratch can be very difficult and requires us to develop some clever exploration methods. This game is not actually difficult to play for a person. You could try it. You can fire up the Atari emulator. You can try playing it. It's not really that hard. There are other games that are quite a bit harder. And the reason it's not that hard for us is because we kind of understand what all the graphics in this game actually mean. We have some prior knowledge that helps us understand that. We know that keys open doors. That's just prior knowledge that we've brought with us before we even started playing the game. We know that ladders are things we can climb, and we don't really know what skulls do. I mean, we kind of know what they do biologically, but we don't really know what a rolling skull does. But because of the symbolism inherent in the game, we kind of guess a priori that a skull is probably not a good thing. Like, it's probably not a bonus that's going to give you a big score if you touch it. Skulls are kind of negative. So our prior understanding of problem structure can help us solve new tasks more quickly. Because even if we don't know exactly how everything works, we have some rough idea that we can use to guide the learning process. So that's basically the aim with transfer learning. So with transfer learning, we're going to try to get our algorithms to use prior knowledge, kind of in the same way that we might use prior knowledge to learn the game more quickly. So perhaps if we want to learn to play Montezuma's Revenge, we might have an easier time of it if we've previously seen the movie Indiana Jones. Because the movie Indiana Jones, even though the mechanics of that movie are completely different, it's not actually about a guy jumping on ladders and jumping over skulls, some of the symbolism might be related. And we might figure out that, well, if you're exploring this ancient ruin, maybe you're looking for treasure and you don't want to get killed by the skull. So if we've solved prior tasks, we can view, watching the movie might be a task. We might acquire useful knowledge for solving a new task later on. So then the big questions we have to answer when we talk about actually designing algorithms for transfer learning is, how is the knowledge actually stored? How do we actually encapsulate the knowledge from past tasks so that it can be useful for new tasks? And there are a bunch of objects that we've already learned about in reinforcement learning that can be used to transfer knowledge. So for example, a Q function or a value function tells us which states are good. So if we figure out Indiana Jones's value function, we might figure out that rolling things are bad because I don't know, maybe this is, I'm showing my age, but in the movie he runs away from a big rolling rock. So things that roll around kind of are negative, they have low value. Things that are shiny and gold colored are positive and have high value. And that's something you can take with you and help you learn the game. Maybe you can transfer your policy. So the policy tells you which actions are potentially useful. Maybe a policy from a different task will not immediately succeed on a new task, but maybe it'll do better than completely random behavior. So perhaps there are some actions that are just never useful. Maybe if you're learning to walk, and then you're learning to walk through a maze, well, just learning to walk even without the maze will teach you not to fall, so you'll just stop falling, and that will already help you get started. And then maybe you can transfer models, predictive models, like in model-based RL, because maybe across different tasks, the laws of physics are conserved, even if the objectives change. So in some cases, transferring models can be really useful. And then the last one, which is maybe a little subtle, but it's actually a very important point, is that perhaps what you want to transfer is not quite as direct. Perhaps what you want to transfer are representations or features, not necessarily functions that directly output actions or Q values or predictions, but simply features that you can then use to build on top of to acquire a policy or Q function in a new domain. This one is a little subtle, but it actually ends up being quite important. So let me illustrate this with some experiments. This is from a paper by Evan Schellhammer called Loss is its own reward. And in this paper, one of the things that Evan studies is what happens if you train Q functions to play Atari games, and then you delete the top layers in the Q function and just retain the convolutional layers. So the convolutional layers can be viewed as feature extractors. They're essentially picking up on Qs in the visual observations that are useful for then calculating the Q values. Once you throw out the top layers in the Q function, you don't have Q values anymore, you just have some features. And what these plots are showing is the black line is when you train on each of the games from scratch, and the red lines are what happens if you train with the convolutional layers initialized from those good networks. Obviously, it's an unfair comparison because the initialization was already trained to play the game, but what it illustrates is that just from initializing those features without actually knowing a priori how to output the correct Q values, the red lines are already learning much, much faster, meaning that acquiring good representations can help you do reinforcement learning more quickly, at least in this case where the representations are sort of the perfect representation in some sense. Okay, so let's go through a little bit of terminology for transfer learning. This is terminology that you'll see come up again and again today and next week. So in transfer learning, you're going to be using experience from one task or set of tasks to learn faster or achieve better performance on a new task. So in reinforcement learning, a task is essentially an MDP. A task is defined as a state space, action space, transition function, reward function. And sometimes we won't change all of these things. Like sometimes we'll want to transfer to a different reward function, but for the same dynamics, or sometimes we'll want to transfer where the reward function stays the same, but the dynamics change. But in the general case, a task is an MDP. So maybe the MDP of watching Indiana Jones is kind of a trivial MDP, so it doesn't make sense to transfer a policy from that, but maybe it might make sense to transfer a representation. So Indiana Jones here is a source domain, and the game is the target domain. So you're transferring from source to target. And you'll see this term used a lot when people talk about transfer learning or multitask learning, which they'll say, oh, we're doing one-shot learning or zero-shot learning. Shot represents the number of attempts in the target domain. So usually when you're doing transfer learning, you're not too concerned with how much you have to interact with the source domain. You sort of assume that there's been a lot of interaction, a lot of learning in the source domain, but you're very concerned with how quickly you can acquire behaviors in the target domain. So you might in particular want to acquire behaviors in the target domain with a minimal amount of interaction. So shot refers to how much interaction. If you see zero shot means without using any experience in the target domain, can we succeed in the target domain? So that basically means generalization. Can you just run a policy that was trained in the source domain in the target domain and succeed? And there are actually things that you can do to improve the probability that this will work. One shot means you try the task just once in the target domain. Usually if you're doing one-shot learning, you can't train a complete policy in the target domain, but perhaps you can get just enough knowledge to adapt a policy or value function or model that was learned in the source domain to the target domain. And then maybe you have few shot, try the task a few times. Or sometimes people will write k shot, means try the task k times. Okay, so what are the different ways that we can frame these transfer learning problems? The first class of transfer learning methods I'm going to discuss are what I'm going to call forward transfer. So forward transfer methods, they train on one task, then they throw out that task, and they retain some kind of model or knowledge, and then they do something on top of that to transfer to a new task. So you interact with the source domain, then you're done with the source domain, you put it away, and then you go and interact with the target domain. I'm going to discuss a few methods. The first one is technically called try it and hope for the best, which is exactly what it sounds like. The second one is be a little clever about the design of your architecture. So perhaps you can design architectures that are especially suited for transfer. And then I'm going to talk about fine-tuning. Next week, I'm going to also discuss multitask transfer, where you train on many tasks, and then you go and you train on the new task. I'm going to talk about how you can get this to work well by being clever about how you choose those many tasks. So if you apply appropriate randomization to the source domains, you can increase the chance that transfer will succeed. I'm going to talk about transfer with model-based reinforcement learning, and I'm going to talk about something called model distillation, as well as contextual policies. So we'll learn about those probably on Wednesday. As well as modular networks, which are networks that share some parameters across different tasks, but not across all the tasks. And then on Friday next week, we'll have a lecture on multitask meta-learning, where we're going to take this multitask transfer idea to the next level by not just learning policies or models, but actually learning entire learning procedures. So you're going to use prior tasks to actually learn how to learn. And we'll talk about RNN-based meta-learning and gradient-based meta-learning. So this is going to be on Friday next week. But in the last portion of today's lecture, let's just start with a discussion of the forward transfer. And I would emphasize here that there is no single solution to the transfer learning problem. So the things that we're going to discuss today and next week, these are all kind of a survey of recent research, and there is not a single answer to a transfer learning problem. It really depends on the problem setting and the kind of technique that works out well for you. So let's start with forward transfer. Try it and hope for the best. Kind of an obvious thing. Sometimes, if your source domain and your target domain are similar enough, things just work. And don't underestimate the chance of things just working. Always try it first to see what happens. So here are a few videos of this. This is a policy that was trained from image observations to put caps on bottles. Now, here, if you want to do the try it and hope for the best, obviously you can't get this to generalize to some completely different bottle or some completely different bottle cap, but maybe you can generalize to an environment where there's some other bottles standing around, and perhaps the robot can figure out which bottle is the right one. Okay. So why does it do that? Well, maybe the design of the neural network encodes some invariances. In this case, this just happens due to the fact that you're using convolutions. Convolutions have spatial invariance, and these kind of distractors end up working out. But of course, it's a very chancy thing, right? Maybe these kinds of bottles work, maybe some other distractor wouldn't have worked. And indeed, that's what happens. So here, if someone is actually holding the bottle in their hand, now things don't work out very well because the color of the sleeve is similar to the color of the robot's arm, and it's never seen the sleeve before. So try it and hope for the best. Exactly what it sounds like. Sometimes it works, sometimes it doesn't. You can do things to improve the chances of this kind of zero-shot approach working out. So for example, here, this is kind of similar experiments, but done using object detectors on top of pixels. And here the robot can transfer to some cups to pour into the cup, but here when there's two cups nearby that it's never seen before, it just pours between them. So sometimes works, sometimes doesn't work, but worth a shot. So sometimes it can save you a bit of effort. But now let's talk about the ways of that we can do forward transfer that are a little bit more principled, that actually we might have some hope would work in a more general setting. The most popular way of doing transfer, at least in supervised learning, is actually fine-tuning, which is the simplest thing you can think of after the try it and hope for the best. You have some data set that's big and hopefully representative of large parts of the world. You train on that data set, and then when you have a new task that you want to solve, you take your model that you trained on this big data set, hoping that it learned good features, and then you basically fine-tune that model. You train for a little bit longer on the new task that you want to solve. So maybe you train a model to detect objects in ImageNet, and now you're going to fine-tune that model, which means just train for a little bit longer on detecting parts of birds. And because parts of birds are similar enough to images in ImageNet, then perhaps this fine-tuning procedure will work. You can extend the same idea to reinforcement learning. So the trouble with reinforcement learning is that there's no such thing as an ImageNet for reinforcement learning. So in computer vision, because ImageNet is a large data set that covers broad swaths of the world, you can train on ImageNet and fine-tune on a different task. In reinforcement learning, we don't have ImageNet, so we have to take a little bit more care to fine-tune. At this point, I'm out of time for the lecture, so I'm going to leave you all with a cliffhanger, and I'm going to tell you about fine-tuning and reinforcement learning actually on Wednesday next week. So I'll see you all then for more transfer learning and multitask learning.